All right, so we're recording now. Uh, Again, I'm sure have a few more participants join in here over the next minute or two. So before we get started working anything, a couple of items I wanted to mention. On Monday, I will send you an email with some more information on HonorLock, and also some information about the test taking procedure. I'll try to send that out an email on Monday. And I was looking right now. My best guess, our first test would be a week from Monday, Monday, June the 15th. Obviously, subject to change depending upon what happens between now and then. But right now, that's my best estimate. Test week from Monday. And before we start working some examples related to shear stress, pause a second. Anybody have any questions about anything you want to ask or? Right, I'm not seeing anybody or hearing anybody ask any questions. So we'll get started. First, remind you what we were discussing yesterday. This was in, I believe, section 1.5, if I remember right. We're talking about shear stress. And notation-wise, tau is what we use to denote shear stress. And remind you in this formula, tau equals V over A here. Tau is the shear stress. V is the shear force, as the force that's parallel or tangent to the cross-sectional surface area. And the denominator A is that cross-sectional surface area. And so that's what we're going to do. We'll spend most of our class time today doing a couple examples. We also remind you, one of the last things we talked about was the difference between what we call single shear and double shear. So if you've got some kind of bolted, pinned, glued joint that's holding two pieces of structure together, one of the things you're got to be able to do is look at that particular type of joint and determine, is it single shear, is it double shear, and what is that shear force V that's actually acting on the fastener. And so the first example we're going to work is going to be along those lines. So let's try to do a problem. And I'll draw the picture in a second, but you're going to see we've got this one member, AC, is attached by a, let's see, it's 10 millimeter diameter bolt to this bracket at C. And we want to find the shear stress on the bolt at C. That's what we're going to hopefully calculate, is what is the shear stress on this bolt at this, you're going to see it's a pin support. And let me draw a picture here. We've got a vertical member that has a pin support. So this is a pin support here at C. And we've got also a cable that's attached to it at point B and goes over here to another support. I think this is D. And it's supposed to be straight across. And up at the top, at point A, we're going to apply a horizontal force of 5 kilonewtons. And we need some dimensions on this. And again, I'll remind you, my pictures never come out to scale. From A to B is supposed to be 1 meter. And from C to B, this is supposed to be 6 meters. And then across horizontally from C to B, looks like 8 meters. All right. So again, we've got this vertical member, AC. We've got a pin support down at the bottom at C, and we've got a cable attached to it that's also supporting it, keeping it upright, preventing it from rotating about that pin support at C. And we're applying this horizontal force at the top. And also, we need a little more information about this pin support at C. Again, going back to what I mentioned a minute ago about single shear and double shear. And so if you look at a side view, so if you look in, say from the right side, what you would see at C is you've got this bracket that's attached, welded to the floor or something. It's fixed. And it looks something like this. All right, so that's what the bracket at C looks like here. And remember, AC fits down in between these two vertical protrusions from that bracket at C. And that's what our bolt goes through that member AC. And so that's what it would look like if you looked at from the side. All right. So before we go any further, make sure if there's any confusion about my picture or anything like that, speak up. Otherwise, we can start our solution to this. All right, no questions. So the first step in all of these problems is just like it was in statics. We got to draw a free body diagram, right? Because we're trying to find what the shear stress is on that bolt. See, we got to know what the force is acting at that bolt at C. So let's draw our free body diagram of this vertical member. Here at A, we got our applied load of 5 kilonewtons. Here at B, we've got the force in that cable, right? Because if we pull on this thing to the right, that cable's going to pull back. That's what's keeping it from rotating over. Again, that cable is a 2-force member. So I know the force, I'll call it force BD. It's going the same direction as the cable. So if this is some angle theta, that's the same angle theta. Now, we could calculate that angle, right? Because we got a nice triangle here. We know 2 sides of the triangle. And we could do inverse tangent, I think 6/8. We could get that. But if you notice, we actually have a special triangle here. All right, this is if this is 6, this is 8, the hypotenuse is 10. It's a 6, 8, 10 triangle, which is the same ratio as a 3, 4, 5 triangle. So it's a special triangle. So I'm going to use that to get my x and y components. So this looks like this would be 4, this would be 3, and that would be 5. So that's what I'm going to use to denote the direction there. And our pin support here at C is always with any pin support, we get two reaction forces, Cx and Cy. Again, this is 6 meters, this is 1 meter. We got our dimensions, we got our three unknown forces, and we have our free body diagram here. Our goal is to find the forces acting at that pin. But in order to do that, we're going to have to also find what the force is in BD here. Otherwise, we're not going to be able to find both Cx and Cy. So again, there's more than one way to get there. If it's me, I'm going to probably start by summing the moments about C. That eliminates these two unknowns, and I find force BD. So let's start there. Sum the moments about C. I choose direction positive, your choice there, counterclockwise, clockwise. But please, get in the habit of indicating which direction you're taking positive to be. So if we sum the moments about point C here, this point right there, again, we eliminate Cx and Cy. The only two things causing a moment is my applied load of phi and this force BD. Now, as far as force BD goes, all of force BD is not causing a moment, right? If we look at this force, if we break it down into horizontal and vertical components, the vertical component goes through C as well. So the only thing causing a moment is this horizontal component, right? And this would be force BD times cosine of that angle theta, which, again, if we're using our ratios there, cosine of that angle is 4/5. So we're going to take force BD times 4/5. Right, that's the force. Now we got to multiply it times the distance from here down to C, which is 6 meters. And we don't need to put the meters in it. And it's causing a counterclockwise moment, which is a positive moment. The 5 kilonewtons up there pulling to the right is causing a clockwise moment. So it'd be a negative 5 times that vertical distance is 7. And we solve for force BD. So we get force BD. I got 7.29 kilonewtons. Right? And it's positive. It is going the direction I assume, which is good because if it's a cable, it doesn't have a choice. That's the only way it could go. But we got a negative there. We know something wasn't right because you can't push a rope or a cable. And so this force is going the direction I assume. But now that we know that force, it's straightforward to just sum the forces in the x and y direction to get Cx and Cy. So let's sum the forces in the x direction. I'm going to take positive to the right. I assume Cx was going to the right, so it'll be positive Cx. Again, the horizontal component of force BD is going to the left, so it'll be minus 7.29 times 4/5. Again, this is force BD there. The 5 kilonewtons is going to the right, so it's positive. And it looks like we've got onto all three forces that are in the horizontal direction included, so solve for Cx. And I got Cx to be 0.832 kilonewtons. Again, positive just indicates it's going the direction I assume. So I assumed it was going to the right. It's going to the right. And then now we sum the forces in the y direction. I assume Cy was going up. Right, the y component of force BD is going down. So it's going to be negative force BD, which was 7.29, times sine of that angle. And sine, being opposite over hypotenuse, would be 3/5. And that's it, right? Our 5 kilonewtons is horizontal. It has no y component. And I guess Cy is, I got 4.374 kilonewtons. Again, positive, it's going the direction I assume, going up. Now, here's where a lot of very common mistake gets made. I see students solve similar problems all the time, and to calculate the shear stress, they use either Cx or Cy. But that's wrong. That's not the total force acting at this joint C. What we actually, all we found are the X and Y components. We need to find what the actual resultant force is, right? What we've actually computed here. You've got this pin support here. Right? We have found Cx and Cy. Right? But what we need to know what the resultant force is. We need to know what this and what angle it's actually acting at. I don't know. We could certainly calculate it. It's not going to be the same as this angle up here. It'll be some unknown angle. I don't know. I'll call it alpha. But really, you'll see it doesn't matter. We don't need to know what angle it's at. But we need to know what that resultant force at C is. Not just Cx or Cy. We need to find both of those in order to calculate that resultant force we get by summing up the squares of the two components, Cx and Cy. That will actually give me the resultant force acting at that pin support at C. So substitute in what we just found, 0.832 squared plus 4.374 squared. Some of those take square root. I got 4.45 kilonewtons. That is the resultant force acting at that pin support. Right? Now, we go back to, we're going to try to find shear stress by V over A. We need to find what V is. It may or may not be this force that we just calculated. That would depend on if this is in single shear or double shear. So looking at our what our pin support looks like, anybody want to volunteer, venture a guess if you remember something?
Double shear.
Which one?
Double shear.
That is correct, right? And we know it's double shear because if we look at this, right, we got this force C here. Well, let me come down here. I'll draw a new picture. Flutter that one up too bad. Right, we've got force C acting on this thing, and we've got this bolt that goes through there. Right, the shear force V, that's the force that's acting on that cross-sectional area of the bolt. We know since forces have to add to zero, that each one of these has got to be half of whatever force C is. So this is what we talked about yesterday, and we would call this double shear. So when we do, say you get the shear stress on this bolt at C, yeah, we're going to take what the shear force is, divide by the cross-sectional area. So we know the shear force V here is what we just found is FC over 2. So we're going to take our 4.45 kilonewtons. I'm going to write this as 4,450 newtons. Right, we divide that by 2, and then we're going to divide by the area. And everybody, this is one of these, what I refer to as should be a commonly known fact that everybody should know what the area of a circle is. Now, most of you probably more familiar with the area of a circle being pi r squared. But you're going to see in this class, in anything related to any kind of structures, if you've got any kind of bolt or pin or rivet, a rod, a cable, the size is almost always given in the diameter. In fact, if you go back to the problem statement, the size of that bolt is the diameter is given, not the radius. And so, again, this would be something, if you don't know already, you got a circle, you got the diameter of the circle, and the area is pi r squared, but the radius being half the diameter, if you substitute that in there, you wind up with pi over 4d squared. So that's something, again, everybody should know. I expect, if you're taking a test, that's formula you're responsible for. You should know that. So to get the area of that bolt, we do pi over 4, and the diameter, if it's 10 millimeters, that would be what? We'll go 1, 2, be 0.01 meters. Is that right? I hope I got my decimal places correct. So 0.01 meters squared. And when you actually take your calculator and punch this in, you're going to get a really big number. Remember, we talked about it's SI units. Newtons per meter squared is what we call a Pascal. And these stresses are going to be really large. And so it's very common to write it as megapascals, which is 10 to the 6 Pascal. So you actually get 28,300,000 something. But I'm just going to go ahead and write it as 28.33 megapascals. This is preferable to writing out 28,333,000 pascals. Okay? So you'll see, again, a lot of the work that's involved in solving this problem is statics. The mechanics of materials part is knowing shear stress is V over A, and knowing that this is double shear, which really is statics in itself, but maybe something new that you didn't necessarily encounter in statics, but still it's static. So really the mechanics of materials part is just plugging in the formula V over A at the end. All right, but any questions about this example? All right, so everybody good? Let's see, I have to pick on somebody different today.
Can you give me a little bit right quick? I'm still copying the last.
Yeah, that's fine. That's why I'm gonna scroll down. I'm gonna find somebody. Avery Claire, you there? Unmute and say hi.
Hi, I'm here.
Okay, I just again like to hear a voice every once in a while. Just checking in. All right. So, not seeing any questions. Everybody got a copy of what you want to copy? We can move on and work another problem. If not, speak up now or forever hold your peace. All right. Well, then we'll move on and see if we can solve a different problem. All right. So this one, again, it's going to be a little bit different. Let's see. Let's start up here. So here, we're actually going to try to find the normal and the shear stress. And not want to focus for me. Come on. There we go. We're going to find the normal. And it went out of focus again. So we're going to find the normal and the shear stress. That is acting on section AA, which will make sense in just a second when I draw a picture. What we've got is just a straight bar that has a rectangular cross section. Work on my 3D drawing skills here. Not super great, but we'll go with it. And we're going to apply an axial load. We're going to pull on this thing with an axial force of 85 pounds. And so back here, let's see, let me do this one. All right, so again, obviously, if it's in equilibrium, and my things, they're supposed to be lined up, but they're not quite exactly lined up there. But you know, we're pulling on each end of this rectangular bar with a force of 85 pounds. And dimensions, again, mine's not to scale. This is it's 3 inches tall, 1 inch wide. And we're going to come in and look at this cross section is at an angle. We're going to slice this thing not straight through, but we're going to slice it at an angle. And again, this will not be to scale because this angle is more than 15 degrees, but it's supposed to slice it here at 15 degrees. So we got this rectangular bar. We're going to come in and slice it at a 15-degree angle. And we want to know what are the normal and shear stress on that cross section. And it may be a little clearer if you can draw much better in 2D. If we look at a 2D picture, again, this is 15 degrees. 85 pounds. And we want, if we're getting the normal and the shear stress, that means we need to know what the normal force is. Right? What's the force perpendicular to that surface? And to get the shear stress, we need to know what the shear force, or the force that's parallel to that surface is. All right. And again, this is 15 degrees. All right, so before we again start doing any calculations or go any further, make sure if any questions are not clear about, I know my picture's not great, but hopefully it's good enough. Everybody understands the setup here and what we got. All right. Well, to get that shear stress and normal stress, as I said just a second ago, we need these two forces, the normal force, the shear force. We also need to know what the area of that surface is, right? When we slice this bar at the angle, that cross section is not going to be 1/3 anymore, right? If we cut it straight through this way, that cross section would look just like the ends. It's a 1/3 rectangle. But we've sliced this thing at an angle. So I'll see if I can draw and attempt this three-dimensional picture here. We actually have That's not too bad. All right, this is 15 degrees. We know the vertical distance here, obviously this is way out of scale. This is 3 inches, and this is 1 inch across here. But this is that's the area. That's my surface area. If we slice this thing at 15 degrees, that's looking at that that surface. All right. So we need to know what that area is. Well, you could get this a couple of ways. One is we could see if we can calculate this distance. Right? This I'll call it C. We got a nice triangle there. That's the hypotenuse. So I know sine of 15, right, is opposite over hypotenuse. That would be 3 over C. So that distance C would be 3 divided by sine of 15. And we'll get a number for that in just a minute. But that's the length of that side. So this area is a rectangle. And so we just multiply length times width. The length on this side is 3 divided by sine of 15. And the length of this side is 1. So that cross-sectional area comes out to be about 11.59 square inches. Any question how we got that cross-sectional area here that this normal force N and shear force V are acting on? All right. So now we just got to figure out what N and V are. Here's where the statics comes in. And we actually have a choice here. We could do this a couple of ways. Right? We could do what a lot of people just by default, always take X and Y to be horizontal and vertical. And we could do that. We could, if we chose our coordinate system, like this, we could get there. But we're going to have to break both the shear force V and the normal force N up into horizontal and vertical components, which is doable. And they're going to show up in both equations. So we got to break two things up into components, and we're going to have to solve two equations, two unknowns. It works, but it's more work. Right? So there's a better way. The better alternative would be to choose our coordinate system. If I can draw this where it's sort of perpendicular. The better choice would be to choose our coordinate system X and Y so that it's parallel to this surface and perpendicular to that surface. So maybe we'll call this Y and we'll call this X. Right. By doing that, we don't have to break either one of those up into components. The only thing we have to break up into component is the 85 pounds. Also, we're only going to get one unknown in each direction, so it prevents us from having to solve a system of equations. So this is 15, this is 15. So this works, but it's more work. Better choice is to choose our coordinate system parallel and perpendicular to our surface. So with that being said, if we sum the forces in what I call the y direction, I define positive y as being up to the left. We've got the normal force N, and then we would have the component of this 85. Now, if we break that up into components, this would be the component in the y direction. It's actually going in the negative y direction. So it'd be minus 85 times sine of 15. And that equals 0. and we can solve and get in. I got 22 pounds. And if we sum the forces in the x direction, I took positive x down to the left. I assumed v was going that direction. The x component of the 85 is going in the negative x direction. And that would be 85 times cosine of 15. Solve for v. I got 82.1 pounds for v. So we've calculated our area up here. We did some statics to calculate what the normal and shear force acting on that cross section are. And now it's just a matter, again, normal stress is going to be that normal force divided by the area. Shear stress is going to be that shear force divided by the area. So plug in what we know. Normal force 22 pounds. Area 11.59. And that comes out to be about 1.9 psi. These are pounds per square inch. Shear stress, A and V was 82.1 pounds over the area. Comes out to be 7.08 psi. Those are pretty low stresses, but we're not told what this material is. So material may be something pretty weak. Obviously, if that was steel, that would be really, really low stresses. But we'll get into that more coming up in a future chapter about the material. Here, questions about how we got our normal stress and our shear stress acting on this particular cross section. All right. Any questions again? Everybody has written down anything you want to write down? If not, speak up. Otherwise, we will continue. Okay. So next thing we're going to talk about, a little bit different. I'm going to shift gears a little bit. And in the next section, 1.6, we're going to talk about what it means when we say allowable stress, and in particular, something called factors of safety. And we'll not have time. I'm pretty confident to finish this discussion today. We only got about 10 more minutes. But we can talk about this a little bit today, and we'll continue tomorrow. And this we need to get into before we start talking about design. What we've talked about at this point was calculating stresses. Where we're headed is to be able to design a structure. Like that first problem we worked today. If we know what the material that bolt's made out of, we want to design it. In other words, we want to calculate how big does that bolt have to be. Right? And that problem we worked today, we were given the size of the bolt and calculated the stress. Where we're headed is going backwards. Right? We want to be able to determine how big a bolt do we need. And what plays into that is what we call allowable stress. Now, there's a couple of different things that would be considered failure. And most people, when you say failure, the first thing comes to mind is breaking. Right? If the structure actually breaks, that is definitely failure. But that's not always what is considered failure. You could have breaking, that would definitely be failure. And this occurs at what we call the ultimate stress. And again, we're going to get into these definitions a little more. I don't remember, chapter 2 or 3. Ultimate stress. So every particular material has a value at which it breaks. That's what we call the ultimate stress. So when the stress in that material reaches that magnitude, the material breaks. But oftentimes, breaking is not necessarily what we consider failure. It could be that you have permanent, I spell it right? P-E-R-M-A-N-E, is that right? Permanent, E-N-T or A-N-T? Permanent. I think it's A, isn't it? All right, somebody's got to be better at spelling than me. Isn't it supposed to be A? Permanent or E? Nobody's going to answer?
I think it's E.
It's an E? Okay. We'll go back to E. It just didn't look right. So if you have permanent deformation, either one of those, a lot of times are considered failure. If you're designing a structure, and you have a load applied to it, most people or engineers who designed it don't want it to permanently deform. Deformation is reality. Everything deforms in the real world. But most things, if it's designed correctly, when you remove the load, it goes back to its original shape. So if you apply a load and something permanently deforms, a lot of times that's considered failure. And if that's the case, this occurs at what we call the yield stress. And we'll denote that sigma subscript y for yield. Right? Well, when we're designing a structure, we don't want either one of those two things to happen. And we over-design it. In other words, where we're headed with this concept of allowable stress is you don't ever want the structure to be at the yield stress, or you definitely don't want it to be at the ultimate stress. You want the actual stress to be less than either one of these two. And that's where what we call allowable stress is what's the maximum stress that this structure is allowed to see. And the reason for that is, to some extent, it should be pretty much common sense. If you're designing a bridge and you expect the heaviest vehicle to drive across this bridge to weigh, I don't know, say 5,000 pounds. Well, you don't want the bridge to break if, say, a vehicle that weighs 5,002 pounds drives across it. That would be pretty dumb and almost guaranteed set yourself up for failure because real life structures are going to see, almost always anyway, at least once in their lifetime, some load larger than what you think they're going to see. And so therefore we design it to be stronger than it's necessary. And that's just mainly for safety reasons. And I actually copied a page out of your textbook. So don't worry about trying to write all this down or anything. This is from your textbook. So if you go to page 46 in your textbook, you'll see this. And these are some of the reasons that they list here as to why we over-design these structures. And just a minute, I'll mention some of these. One, like these examples we've been working with, we put dimensions on there. But in the real world, if I've got I forget the example we did, was it 10 millimeter bolt? Well, we did our calculations based on the fact that bolt was 10 millimeters in diameter. But if you go take a bolt off the shelf and actually measure it, maybe it's not exactly 10 millimeters. Maybe it's like 9.7 or 9.6. You can't, depend upon how much money you want to pay, because the closer, the smaller the word I'm looking for. I can't think of it off the top of my head right now. But tolerance. There you go. The smaller the tolerance, the more it costs. The next one down here is more about the loadings that I talked about. If you have some unknown loads you weren't counting on. Another one, over time materials deteriorate. It may not be quite as strong as it was when you first built this thing. And then finally, one of the other ones, some materials, they give some examples: wood, concrete, you've got composites. Their material properties vary. What you find when you look in a table to get material properties, it's kind of an average value. And what you actually have could be a little bit stronger or it could be a little bit weaker. And so we have all these unknown possibilities in there. So that's why it's good engineering practice to over-design a structure somewhat. Right? So this leads us to what we call factor safety. And we'll define what factor safety is, and then it will probably be a good place to stop there. But let's see. Get back to where I was here. Yeah. So factor safety. Which from this point forward, again, we're going to abbreviate FS. Basically what this is whatever you consider the failure stress to be divided by what the actual stress is. So if you're talking about normal stress, the factor of safety could be on either yield or ultimate stress. The factor of safety on yield would be whatever the yield stress for that material is divided by what the actual stress is. Factor of safety on ultimate would be the ultimate stress. That's the stress it's going to break at divided by the actual stress. And similar thing if you're doing shear stress. Factor of safety for shear stress is almost always ultimate. Whatever the ultimate shear stress is divided by what the actual shear stress is. I've seen some material sources that will give you a yield stress for shear, but almost never. The reason being, most things, typically you're not going to get permanent deformation. If it fails due to shear stress, it's probably going to reach a point where it starts to deform, it's going to break. So that's why typically if it's related to shear stress, it's almost always the ultimate. Now, last thing I'll mention, so let's do this and we'll wrap this up here. So that's how, if you wanted to calculate the factor of safety, that's how you would get it. Where we're headed with design is we're going to be given a required factor of safety. Right? So if you've got a factor of safety that's required, then your allowable stress is going to be, we'll call it sigma allowable. Again, it's whatever what you deem to be the failure stress divided by the factor of safety. So if you got a required factor of safety on yield, then you would do the yield stress divided by that factor of safety. That tells you the maximum stress that this structure is allowed to see. So just a for example here. A36 steel. This is just your most basic common structural steel. What most typical buildings you see steel beams and stuff. It's almost always A36 steel. A36 steel has a yield strength of 36 KSI. So if the stress hits 36 KSI, that A36 steel is going to have permanent deformation. So two different scenarios. If you've got, say, the actual stress is, I don't say 12 KSI. So you got a structure, you analyze it, and you calculate that the actual stress is 12 KSI. Then your factor of safety on yield would be the yield strength or yield stress of that material divided by your actual stress. And I think I chose good numbers. That's what, 3? That would be your factor of safety on yield for that particular structure. Or say you had a factor of safety on yield of, say we'll make the math easy, 2 is required. Right? So wherever you work, and we'll talk about this some first class on Monday, wherever you work is going to set what these required factors of safety are. But say you've got a factor of safety on yield of 2 is required, then your allowable stress would be whatever the yield stress is divided by that factor of safety, which would be 18 KSI. So that is what you design your structure to. You cannot have a stress larger than 18 KSI. Otherwise, you would not meet the required factor of safety of 2. Right? So just conceptually, does that make sense? The concept of factor of safety and allowable stress. It's not real complicated, but it's something that most of you probably haven't seen before. So it may take a little bit to digest that. But any questions you think of right now related to factor of safety, allowable stress? We'll talk about it some more tomorrow. Not tomorrow. Tomorrow's Saturday. I'm not going to talk about it tomorrow. I'll probably be cutting grass tomorrow. Monday, we'll talk some more about factors of safety, allowable stress, and then actually get into, okay, now that we know that, how do we design a structure? All right, so we're a couple of minutes past, so I'm going to stop recording here. If there's anybody that's got a question, you want to stick around after I turn the recording off, I will hang around for a minute or two. So if somebody has questions or something you want to discuss, we'll do so. Otherwise, we'll see everybody Monday.